back. Welcome back, everybody. I hope you enjoyed your lunch and did some networking and are refreshed and pumped for the next session. So our next speaker is Zineb. She's an ML engineer at Fever Energy. Her expertise area is time series forecasting. So she's an expert in making forecasting ML pipelines. She has also done some research in this area and published in that area. So today she's going to talk about how time series forecasting will be used for a greener energy. Welcome, Zineb Senane.
Hello, everyone. I'm glad and happy to be here today to give a talk and present how time series forecasting could be is the most important tool to contribute to a greener future. Before getting started, I'm going to give you a brief introduction about my background. I hold a double degree in Master of Science in Engineering. My major was computer science and machine learning from Telecom Paris and KTH. And I have done also some research work on time series, specifically time series representation learning. And this work was accepted and published at KDD 2024. And today, I'm a machine learning engineer at Fever, mainly focusing on building data pipelines and forecasting model. And before getting started, I'm going to give you a highlight of what Fever is doing and what is Fever's mission. So if we think about the power grid, there is a rule that it should be always in balance. And by balance, I mean that energy production should always match energy consumption. But there is a lot of energy that is coming from wind farms and hydro and solar. And this green energy introduces more volatility into the grid, and then it makes it a bit harder or challenging to keep the grid in balance. And our goal is to manage some energy assets and controlling them in order to enable more greener energy. So this means that when we have a lot of green energy on the grid, we can let these assets consume that energy. And also, if there is not a lot of energy, then we can release that energy if it has been stored before. And yes, so again, Fever unlocks and controls this energy flexibility, and hence it makes the energy system in balance, and it enables the use of the more use of greener energy. And as an example, we can think of electrical vehicles. So if production is less than the consumption, then we can reduce the load. And by this, I mean we can send some signal to EV chargers and we ask them to stop charging. If production is more than consumption, then we can increase the load on the grid, and we can ask the chargers to start charging. And in order to do this, there is a prediction problem under the hood. We always need to know how much load we can either consume or we can stop or remove from the grid. And how the business works, there are bets that needs to be placed many hours before. It might be between 24 and 36 hours in advance. So now let's get started, and this talk will be about time series forecasting. And as I said before, time series forecasting is really essential for us to ensure that we have a balanced grid. The agenda for today is as follows. So I'm going to first introduce our use case. What problem are we trying to solve? How did we solve it? And what are the metrics that we have used to evaluate whether we did good or bad? Then it's going to be some sort of lecture introducing time series and what are the different models or approaches that could be used. Some of them might be very basic to the audience, but I think it's good to give an introduction so that everyone would understand what is presented. And we will end up this presentation by a Q&A session. Yes, so the question that we want to answer here is how time series forecasting could contribute to a greener future. And this is the case for controlling EV chargers. So we have a lot of chargers. Those EV chargers, they would send us a lot of events. And then our goal is to collect these events, to process them and aggregate the load that all these EVs together could create. And then we do capacity modeling or time series forecasting to know how much load we would have in the future that we could participate with. And here is, for example, an example. We have a car that is charging, and it says that my charging speed at this time is 500 watts. And then we collect these events, and there is some processing that needs to be that needs to take place. And we need to handle chargers timeouts. For example, we have an EV that doesn't send us more events anymore, then maybe it doesn't contribute to the load that is aggregated at the end. So we need to remove the load that it has sent us before from the aggregation. And yes, the main goal of this part is to aggregate the load that we have for every hour from all these EVs, and that load that we can put for balancing markets. And all the above is done in a batch processing, and we need to create load for every hour, and this is done hourly. The next step, once we have our data, which is hourly load, we can start training some time series model to do the forecasting part. Our goal is to forecast 24 hours for day-ahead market participation. So we need to forecast 24 timestamps. But this forecast needs to be available a few hours before. So we need to forecast more than 24 timestamps. And as of now, we are using quite a few libraries to do so. We have Optuna for hyperparameters tuning. We have Nixla for trying out some deep learning forecasting models, and Autoglone also for pre-trained forecasting models. So now that we know what is the use case, what are the challenges that we are still facing? So there are quite a lot of uncertainties in charging behavior. As an example, and I have already mentioned this one, is what if a charger stops unexpectedly? Should we then consider this in the forecast? Should we take it out from the load? And the second one is some external forecast, which it could be weather, for example. So what if it's a snowing day? Should we expect people to charge their cars? Would they drive or not? And also, if it's a holiday, then do they need to charge it quite a lot because they might drive for a longer distance? The latter is still an open question to us, and we don't know how to deal with that yet. For the first one, there is this timeout logic that we have already in place. And when it comes to evaluation metrics, so now you have your training data, you have different models that you have trained, and you have the forecast. How do you select or evaluate which model works best for your use case? We are adopting quite a standard matrix, which is mean absolute error and mean squared error. And we also have overprediction and underprediction rates. So overprediction is when you predict more than what you have, and underprediction is when you predict less. And which metric among these two you need to pay attention more, it depends really on the use case, whether you need to be more conservative or it's fine if you take a bit of risk. And finally, we have also business metric. And this one relates mainly to how accurate you are in your forecasting and how much load you could capture. Because the most load you capture, the most money you could earn from your participation in balancing markets. Now that we are done with the use case, I'm going to move into the lecture style part. And let's start with the time series data. So time series data is basically a variable that is recorded over time, and we have three different types. Univariate, it's only one time series. Then we have multiple time series, which are a lot that are recorded at the same time, but maybe there are no correlations or dependencies between them. And finally, we have multivariate, which is many time series that are recorded over time, but there are some interdependencies between them. As an example, for time series, we can think of water consumption and electricity consumption in a household. They are not correlated. For the multivariate, we can take of recording vital signals of a patient, for example. Next, sometimes we are like interested in forecasting only one time series. It's univariate time series forecasting, but still there are like other time series that they could be useful and informative, and they could boost the forecasting performance. And these are called exogenous variables. And if we look here at this graph, what we have in black is our target variable. So that is what we are interested in forecasting. But we are using another exogenous variable. And this one, as you can see, has a negative correlation with our target variable. So now let's move on to what models we could use. And I'm going to start with the basic ones, the statistical methods. And here I only mentioned 4 of them. So we have, first of all, smoothing moving average. You take a window of your data and then you compute the average over that window and you use that as a forecast. It is quite basic and it only captures the short-term fluctuations. Second, we have exponential moving average, and this one is quite similar to smoothing moving average, but you apply a decaying weight to past data, so you give more importance to recent data. And this one captures better long-term trends. And then we have ARIMA. ARIMA assumes that the data is stationary and it's also an autoregressive model. And it applies some differencing. So it takes a value at some timestamp and it deducts the previous value from it. And this one is good at capturing short-term fluctuations and only the long-term trend. And finally, we have profit. I think a lot of industries, they do adopt this model in their time series forecasting pipelines, and it decomposes the input into trend, seasonality, and holidays, and it is quite easy to use, and it enables the user to apply different seasonalities like yearly, weekly, monthly, and so on. Depends also on the frequency of your data. And it also makes it easier to employ different holiday effects. But the question is, are these statistical models actually really useful when it comes to real-world time series forecasting cases? And I personally think that that is not the case. Most of the times, they do not support exogenous variable, or there is a limited support for that. And profit is even that it supports exogenous variables, it's still not, it doesn't give a good performance, and it's not ideal, and it most of the times tends to oversimplify the time series patterns. So what else could we use? We have some ML models that we can train. And I see machine learning models as like 2 different approaches. So the first one is regression-based approach. And in this part, we do think of time series forecasting as if we are solving a regression problem. And we can employ as many exogenous variables as we would like to. And we can also use lagged values as features. So if we look at this example, we are using 2 past values as features, and we are using one weather feature and one time feature. And our goal is to predict the next timestamp. An example of this is boosted trees. And here I listed 3 main ones, LightGBM. This one, when it tries to optimize this forecasting or like regression part, it goes through the leaves. It doesn't develop level by level. And hence, it is more prone to overfitting, but it is fast. The second one is XGBoost. So it tries to develop all the nodes at each level before moving forward to another level. And this one, it is more robust if we compare it to LightGBM to overfitting, but it is slightly slower. And finally, we have CatBoost, which is kind of similar to XGBoost, but it handles categorical features. So you don't need to do any feature engineering if you have a categorical feature. You just need to specify those, and the work is done for you. Second, we have window-based approach. And for this one, if we look here at this graph, we have our target variable or target time series. That's what we are trying to predict, and it is in black. And then the dashed ones are exogenous variables that could be helpful in our forecasting. And one of them, we could see that it is also available in the future. We can think of this as time feature, for example, because we know if we are predicting for the next X timestamps, we know what are these timestamps, and we can have those time features. And the goal here is to take this history window, which is on the left side of that vertical dashed line, and we are trying to predict the target variable on the right hand side of this graph. So our input to such models would be a matrix, 2D matrix, and then the output is 1D vector. And here is an example of such a model. Temporal fusion transformer. This model is developed by Google, and it takes as input what I showed before in the graph on the left side. So it has static variates, historical features, and future features. And let me now give you an example of what the static variates could be. So imagine if you have a product that you are selling, right? In different regions. So region in this case doesn't really depend on the time. So that is a static variate. And then historical features is whatever information is available from your time series in the past, and future features could be, for example, weather forecast, it could be time features, and so on. And this model is composed of 3 main blocks. So we have first static covariate encoder. And this one, it takes as input the static covariates, and then it tries to transform them into context that could be useful for the latter 2 blocks. Second, we have the temporal covariate encoder, and this one, it processes the time-dependent variable. So it takes both historical features and future features, and it tries to learn the long-term dependencies between the different timestamps within our, or like between our history and future. And finally, we have temporal fusion decoder, and this one, it takes all the encoded inputs and some context from the first one, and it applies the attention mechanism on the encoded inputs. This model, if you want to try it out, there is an implementation and a good documentation in Nixla in the neural forecast library, which is quite kind of handy if you want to start with it. Okay, so now that we have gone through what we could use when we do time series forecasting, I'm going to just try to wrap up and give you like a highlight of the results that we have gotten from our modeling part. So we have tried few models, and these are this is the margin of improving our metrics. So we have lowered the mean absolute error by 27%. We have lowered the MSE by 34%, and we have also reduced the underpredictions rate by 7.5%, and we have increased the accuracy of the load that is captured by 10%. But we have introduced a slight overprediction, so all this improvement was at the cost of introducing some overpredictions, but it is only 1.4%. Yes, so now to wrap up, the main thing, or like the main takeaway from this presentation, is that maybe statistical model, it's not the way to go if you are doing time series forecasting. Maybe it's better to try out new models, deep learning models. Maybe it is worth it. It could give you a boost in performance. And you should always think of what metrics and define them for your business use case, and try to improve on all of those and not only the standard errors. Thank you all for your attention.
Thank you, Zineb, for the nice talk. So, is there any questions from the audience?
Thank you. Super interesting chat. I feel like that, yeah. I feel like it's always a trade-off between statistical and more machine learning, non-parametric approaches.
Yeah.
And then it's often like at the cost of like interpretability. So do you have anything that, you know, how did you approach that? Is there like, yeah, how did you approach like understanding how your model predicts?
So we have defined those metrics that we always keep look at to understand whether like we are doing good or bad. And for us, like these are good indicators of how good the model is good or not. And also when we were selecting like what models to try out, TFT, for example, the one that I mentioned at the end, that one is also explainable. You can also get feature importance from it. Yes, so the models are explainable. You can look at different feature importance. You know whether, okay, the feature that is ranked as the most important makes sense or not with regards to your use case. And also the metrics that you are defined, are they improved or not? So these are, I think, the two good indicators of whether what you are doing is good and whether it is explainable or not.
Thank you. Any other question? Yes.
Thank you for the great talk. I have a question regarding the features. So let's say for the main time series, how do you select the window? For how long back we should look at the data? And when it comes to the lags, which lags are relevant even for the machine learning model, not the statistical model? Thank you.
That is a good question. So if you want to select like, okay, how long or like how long the look back window should be, I think that it also depends on like what are the seasonalities that you have in your data. Is it like daily? So then maybe a few days would be enough. Is it weekly? Then in this case, you need definitely to take a few weeks. Is it monthly? Then you should consider longer window. So that is one of the things that we need to keep in mind whether when selecting how long should be our history, its seasonalities. And your second question was about lagged values. Okay, so if you have a value, for example, when it's like a regression style forecasting, then you need to pick the values that are more relevant to that hour. And here again, it's the same thing, but it's not seasonality, it's more like periodicity. Do you see the same thing every hour, or like does it depend? For example, I don't know, you have a trend and you could see that you have the same patterns for the same few hours every day, something like that. Then it is more useful to pick those hours as lagged values and features for your model.
Thank you.
Thanks for the presentation. I have a question about the windowing again. So if you have chosen a particular window, we know that we have temporal dependencies in time series data. So for evaluating your performance metrics that you have chosen, did you choose window-based or did you collate everything together as one historical window?
So we do have like few windows that we are using as a history in order to get predictions. And when it comes to the evaluation, we took the horizon windows and we gathered them for like over, I think it's like a month and a half, the metrics that I showed here, and we average over that window. It's like a month of predictions, but the predictions not, you do it at once for an entire month. You do it daily for a few hours.
Okay.
24 hours to be more precise.
Hi, thank you for your presentation. It was very, I like it because it's what I'm doing, but in another business process. So my question is also about the explainable prediction parts. I'd like to know what kind of models or techniques do you use to do the explainable prediction part. Currently, I'm using Sharply and I'm considered to use NLP as well. So I wanted to learn more about it. Thank you.
When it comes to explainability, or at least what like we have tried so far, is just to look at those weights or like feature importance. We haven't used Shapley or anything else. Yeah. Sorry, I can't hear you.
Sorry, I'm very interested in this question, so I'd like to learn more. How important do you think that to apply explainable prediction features in the data science world, or when we do the prediction models? Because I know some of the users or the stakeholders might cannot understand all those technical terms. So we need, especially for the machine learning models, some users, when they look at the visualization data, then there might not be any data scientists around them. So they need to understand what this prediction is about, where the data come from. So then they might have a lot of questions. So how important do you think that the explainable predictions is when we do this machine learning models?
That's an interesting open question, I would say. I think it is very useful, but again, sometimes you can't really apply those explainable methods. For example, when it comes to deep learning model, then maybe you are not even able to apply those methods and know whether your predictions are explainable or not. But I think it is, if it is possible to have them, I think it's going to be useful, and it's going to give you more insights about how good or bad your predictions are, and you can understand.
Yes, we have a couple of questions from our online community. Have you managed to succeed better on the balanced market thanks to this improved model?
And here there should be like a definition of what is success in the balancing market. But I mean, we have of course improved the accuracy of our forecast, and we have succeed to put more load on the balancing markets and earn more money.
Yes, so then the answer is yes. Here is the next one. Which libraries do you recommend for beginners in applying ML to time series forecasting?
So if you want to just start with something that is already pre-trained, you don't want to train it or anything, I would recommend AutoGluon. It has some pre-trained time series forecasting models. If you want to try to train a bit, but you want to have like all the implementation and some framework that is easy to use, I would then recommend the Neural for Forecast library.
Thank you. Have you investigated any way to improve the models without increasing the overprediction? Or what is the biggest obstacle for this?
I mean, for us, we were tolerating. I mean, we could, of course, either keep the overpredictions as they were or lower them a bit, but then we want to probably capture more load by 10% and improve the other metrics by quite like a bigger margin. Yeah.
Yes, we have time for one more question from Slido. How do you handle schema evaluation systematically for time series?
How do you handle what?
Schema evaluation.
What does schema evaluation mean?
So we can go to the next one in that case. So what do you think is most important, type of model or feature?
It's both. So feature is definitely really important because that is what has the predictive power of whatever you are predicting. So it should be something that is relevant for your target. That is definitely really, really important. And then also what model would be suitable for handling the type of features that you have. So both of them, they are really important.
Thank you, Zineb, again. And we have a small
Thank
gift for you as well.
Thank you.